quantum theory and the electronic structure of atoms. Energy moves through space in waves. Energy transfer is called electromagnetic radiation, and all types of electromagnetic radiation are described in terms of frequency and wavelength. So let's look at a diagram of a wave here. I have denoted wavelength on the wave. Wavelength, lambda, is the distance between any two successive crests. It's one complete wave cycle. Frequency, the symbol is nu, is the number of wave crests that pass a point per given time. One of the main equations that we're going to use for electromagnetic radiation is C equals lambda nu. C is the speed of light, 3 times 10 to the 8th meters per second. That is constant. We're going to set that equal to the product of wavelength times frequency. Another property of waves that we can measure is the amplitude, which is just the wave height. Wavelength is often expressed in either angstroms, which is 10 to the negative 10th meters, or in nanometers, which is 10 to the negative 9th meters, because these quantities are so small. Here's the electromagnetic spectrum. You'll notice that we start off with very high energy on the left over here, high energy, gamma rays, and then X-rays, and then ultraviolet, and we go to very low energy over here with radio waves. High energy has short wavelengths, low energy has long wavelengths. The only portion of the electromagnetic spectrum that we can see is the visible light, and that goes from 390 to 770 nanometers. That's the only portion that we can actually see with our eye. Okay, in this problem, most of the light emitted by sodium has a wavelength of 589 nanometers. What is the frequency? Again, one of the most common equations that we will use is C equals lambda nu. I want to solve for frequency. I want to solve for nu. So I'm going to rearrange C divided by wavelength. C is the speed of light. Speed of light is constant. 3 times 10 to the 8th meters per second. Speed of light is in meters, so my wavelength also needs to be in meters. So we need to do a conversion there, 589 nanometers. Nano is 10 to the negative 9th. So make sure you do that conversion to meters before you solve. So the frequency of this radiation comes out to be 5.09, and then it's times 10 to the 14th. The units are either reciprocal seconds, 1 over s, or frequency is also measured in hertz. Those are the same units, 1 over s or hertz. As light passes from one medium to another, it's bent or refracted. White light, like sunlight, contains light of many different colors and wavelengths. When light waves of different wavelengths are refracted differently when they are passed through a prism or diffraction grating. So what happens is if I have white light that passes through a prism, as in this example right here, you will see that it refracts those wavelengths differently. Red gets refracted the least because it has the highest wavelength. And what you will get when you have white light is a rainbow of colors. It's called a continuous spectrum that you will see. Red, orange, yellow, green, blue, indigo, and violets. Now the light emitted by heated substances produces a series of colored lines called a line spectrum when passed through a prism. The line spectrum for each element is different from every other element, so we can identify elements based on their line spectrum, what colors those elements produce. Hydrogen's line spectrum was studied extensively because hydrogen has 1 electron. And it's shown that the frequencies of light emitted by hydrogen can be predicted by this equation. Now, we will use this equation later, and I'll go through some examples, so I will explain it. R is a constant, C is the speed of light, N is an integer, N is the energy level that that electron is jumping to and from. And again, we'll go through examples with this equation later, so don't worry about it too much right now. In 1900, Max Planck proposed that energy, like matter, is discontinuous and consists of discrete units called quanta. And he said a system can gain or lose energy by gaining or losing a quantum of energy. And he related it in this equation, E equals h nu. So the energy emitted by a photon of light is equal to h, which is Planck's constant, times the frequency of light. So there's two equations that we're going to use, predominantly this one and the C equals lambda nu equation. And you'll notice frequency is in both of these equations. It can be shown that when a beam of light strikes a metal surface, it will cause electrons to be emitted from the metal. This is called the photoelectric effect. Now the number of electrons depends on the intensity of the light, but the energies of the electrons depend only on the frequency of the light. Albert Einstein proposed that electromagnetic radiation has particle-like characteristics, and he called these particles photons, and they possess an energy given by Planck's equation, E equals h nu. So let's look at this problem here. I want to know the energy of one photon of light. Energy of one photon, one particle of light. So I'm going to take E equals h nu. H is Planck's constant, 6.626. 10 to the negative 34th. The units are joules times second. The frequency given as 4.2. 10 to the 14th, that's 1 over s, so the seconds will cancel. The energy of one photon is going to be in joules. And when I solve this, the energy of one photon comes out to 2.8, 10 to the negative 19th joules. Now, according to accepted theories of physics, an electron must accelerate constantly in revolving about the nucleus. In doing so, it would give off energy and spiral into the nucleus. But Niels Bohr proposed an explanation for this dilemma in 1913, and he came up with his model for the atom. He said there is only a certain set of allowable orbits for an electron in a hydrogen atom. And so basically, here's what Niels Bohr said. You have your nucleus, where your protons are at, and your neutrons. And then you have these allowable orbits outside the nucleus. This is where your electrons are at. These are stationary states. So your electrons are in these stationary states about the nucleus. An electron can pass from one stationary state to another. So it could jump to higher levels, it can jump to lower levels. And in such transitions, fixed discrete quantities of energy are involved in accordance with Planck's equation. So electrons can jump from close to the nucleus to farther away from the nucleus, and they can also come back closer to the nucleus. So here's kind of what it looked like for the Bohr model. As electrons absorb energy, they get excited, they move to higher levels. So they move further from the nucleus. And as they come back down closer to the nucleus, they emit light. Bohr was able to show that the frequencies of light emitted by hydrogen can be predicted by this equation. This is the same equation we saw earlier, and again I will explain this. This only works for hydrogen, though. It does not work for any species with more than one electron. So the Bohr model could explain the spectrum of hydrogen and species containing one electron, which is very few, but it could not explain the observed spectra of the more complex species. If you have more than one electron, it did not work. So the Bohr model works for hydrogen, great. It did not work for anything with two or more electrons. At the beginning of the century, light and other kinds of electromagnetic radiation were considered to possess wave-like properties. To explain the photoelectric effect, Einstein was required to think of photons as if they were particles, so we have this dual nature of light. Light behaves as photons, which are particles. It can also behave as waves. De Broglie considered the nature of light and offered the proposition not only does light display particle-like characteristics, but small particles display wave-like properties. Now this is the de Broglie equation. The wavelength is equal to h over mv. Now in this case, m is mass, and the mass has to be in kilograms in order for this to work. And v is velocity, and velocity has to be in meters per second in order for the de Broglie equation to work. So de Broglie said that small particles move in waves. So when you throw a baseball, it moves in a wave. Now we're unable to see the wave-like motion of the baseball because the mass is too large. But everything moves in waves. All moving particles move in waves. And experiments involving the diffraction of electrons have verified that this equation, the de Broglie equation, h over mv, is correct.